In this lesson, we will calculate the thermal efficiency of a steam power cycle. So we're going to look at the steam power cycle. We're going to look at an ideal Rankine cycle, similar to what we did in a previous learning objective. And for this problem, we're going to look at a problem where it comes in as saturated liquid to the pump at 100 kilopascals and as saturated vapor into the turbine at 5 millipascals, and it's asking us to determine the thermal efficiency of the cycle. So let's start off by looking at stating the initial conditions of what we have. We know that the quality is going to be 0 at state 1 because it's a saturated liquid, and we know the pressure at state 1 is going to be 100 kilopascals. Similarly, at state 3, we know that the quality is going to be 1, and that the pressure is going to be 5 megapascals. Now, we can make the assumption, not really assumption, we can tell that the state 2s is going to be equal to state 1 because this is a ideal system, so the pump is going to be isentropic. We can also figure out something about state 2s because we know that this boiler, because it's an ideal Rankine cycle, is going to be isobaric. So since it's isobaric, pressure at 2s is going to be the same as pressure at 3. So that gives us state 2. So then we look at state 4s down here. Again, this turbine, also isentropic, so the entropy at state 4s is going to equal the entropy at state 3. And that condenser down at the bottom is isobaric, so the pressure at state 4s is equal to pressure at 1. So we're getting the pressure going across the isobaric processes, we're getting the entropies going across the isentropic processes. We'll make some assumptions that it's going to be a steady, ideal, one in and one exit system. So when we do the analysis, there's two ways we can look at the efficiency of this cycle. It's a power cycle. So first we can look at is work net is equal to over heat transfer in is going to equal our efficiency. And in this case, our work net is the two work processes. We have the pump, we have the turbine, and our heat transfer coming in is going to come in through the boiler. Or, knowing that the work net, total work, is going to have to equal to the total heat transfer of our system, we could rewrite this as our efficiency is equal to 1 plus the heat transfer going out over the heat transfer in, which in this case is going to be the heat transfer going out is at the condenser, heat transfer in is at the boiler. We're going to start with the bottom one. But I encourage you, after this is done, to go back and try and use this first process using the work net and verify that you get the same answer as how we calculate it here. Okay, so let's start working this problem. So we're going to use this equation. The efficiency of our cycle equal 1 plus the heat transfer being rejected at the condenser over the heat transfer coming at the boiler. So really, based on previous equations where we learned what these values would be for these ideal processes, we know that we can substitute in these changes in enthalpy, right? So now we really just need to find the enthalpy at each of these four states. So we'll start with state 1. For state 1, we're going to use table 11. And table 11, we're going to go down and we're going to look at the row that has pressure at 100 kilopascals. And since we know that the quality is at 0, that means that all of our values are going to be at the saturated liquid line. So our enthalpy at state 1 is equal to the enthalpy at saturated liquid at 100 kilopascals, which is 417.46 kilojoules per kilogram. We're also going to grab the entropy at state 1 because we're going to need it for entropy at state 2s. So the entropy at state 1 is also the entropy at saturated liquid, so 1.3026 kilojoules per kilogram Kelvin. So now we go to state 2, 2s. Now, normally we'd use the compressed liquid rule, but we don't have the temperature here, so we're going to use table 13, which is our compressed liquid tables. If we look at table 13 at pressure of 5 megapascals, now if you go down and look at the entropy values, there's an entropy value for 1.303. So 1.303, that's pretty close to to our 1.3026, close enough within error. So we're going to go ahead and use that as our value. So we're going with the, basically going to assume it's about a temperature of 100 degrees Celsius. So using that as our value, we can look over and we can see that our enthalpy is 422.72 kilojoules per kilogram. Okay. So that gives us our enthalpy at state 2. We're going to go to state 3. State 3, we're going to use table 11 again because we know it's in the saturated mixture region. It's actually on the saturated vapor line at pressure equal to 5 megapascals. So at the saturated vapor values, enthalpy subset G, we get an enthalpy of 2,794.3 kilojoules per kilogram. And again, we're going to look up the entropy at state 3 because we're going to use it down here for 4S. So our entropy at state 3 is 5.9734 kilojoules per kilogram Kelvin. Now for state 4, unfortunately it's not right next to a value, but it is in the saturated mixture region. So we're going to have to, we know it's going to be somewhere in the mixture region. It's in between the vapor line and the liquid line. So we're going to use our table 4.1 with our quality relations. If we look here on the left side, given these entropy values, the entropy that we have, entropy of a liquid, and entropy of a vapor, we can figure out the quality. So plugging those values in, what we get is a quality of 0.771. And if you want, go ahead and pause right now, and you can verify you can do some of these calculations yourself. And go ahead and then let's replay this if you want to check your answers with what I came up with. And then we're going to plug this quality into our enthalpy equation. You can either use the first or the second one, whichever one. If you want to use the differences between the enthalpy at saturated vapor and enthalpy at saturated liquid, or if you're going to use the enthalpy evaporation, you can use that. Either one will give you the right answer, and what you'll get is enthalpy at 4S is equal to 2,158.4 kilojoules per kilogram. Okay, so now we have all the enthalpies at every state. So we're just going to substitute them in to this equation we came up with for our thermal efficiency. We substitute those values in. We're first going to take the difference between the two for the numerator and the denominator, and what we get is negative 1,740.94 kilojoules per kilogram divided by 2,371.58 kilojoules per kilogram. That gives us a ratio of 0.734, and we have that 1 minus it. So what we're going to get then is a thermal efficiency of 26.6%. Now that may seem low. I mean, this is the ideal, this is the best case you can get. But also consider the fact we didn't really heat it up a lot. We just got up to the saturated vapor line. So it's based on what we've put into this system. This is as efficient as we can get. You're going to have different values, but this is around 30% is not that unreasonable an answer for your efficiency of your system. Now I encourage you to go back and see if you can work that problem yourself, but this time use the work equation and seeing if you can get the same thing.